Hello everyone, welcome to the lecture number 46 of this NPTEL lecture series on charging infrastructure, and today we will discuss the continuation of our discussions which we are doing in the last lectures related to transformer design. So, in the last class we have studied about the core loss, which is given by P core is equals to K core into del B raised to power beta ACLC, where beta is your peak AC flux density. So, what it indicates that our P core is directly proportional to del B raised to power beta, where beta is nothing but the material property which goes from 2.5 to 2.7 for the ferrite material. And then we moved ahead our discussion and see the things related to maximum flux density. What we obtain is that the maximum flux density is nothing but equal to the flux linkage with the winding 1 divided by 2 N1 AC, where N1 is the number of turns of the winding number 1 and AC is the area of the cross section of the core. Now from this, from using this particular relationship, what we can get is we will get N1 to be equal to nothing but lambda 1 by 2 delta B AC. Now we know that core loss is dependent on the delta B or the peak AC flux density. Similarly, if we see our total copper loss in the winding, because the copper loss is happening in the winding. So, the winding losses, if you see the winding loss, it is nothing but this particular relationship where we see that our PCU total is actually inversely proportional to del B square. Now, that indicates that if we increase our peak AC flux density, that means if we increase our flux swing in a core, what it indicates that it will increase our core loss. At the same time, it will reduce our copper loss in the winding. So, we need to find out, if we see from this particular curve, there is a curve between the losses versus delta B or the peak value of AC flux density. What we see is that as our delta B increases, our PCU total reduces while our core loss increases, and that is why if we see the overall losses, which is P total. So, we can say our P total is nothing but our PCU total plus P core. What we will see is that it will reduce, and then again after certain point it will start increasing. That means there is a point called as the optimum value of peak AC flux density, where our total transformer losses, or which is comprises of the core loss and the winding loss, is minimal, and we need to find out this minimal optimum value of delta B, that we can obtain by just differentiating this P total with respect to our del B value and make it equal to 0, which will give us the optimum value of delta B, for which our P total is the minimal. And for that condition, if we do this particular expression here, we will get a condition which is nothing but differentiation of core loss versus del B is equals to nothing but minus of differentiation of PCU total with respect to del B, and that will nothing but give us the optimum value of delta B. Now, this is one way of doing the optimization of or obtaining optimum value of delta B. You can do further advanced level of optimization to further obtain the best possible delta B, for which the overall power losses in the transformer is minimal. Now, along with that, we have also seen that in the winding losses, we have seen that there is a term called as a gamma j, which is the fraction of the area allotted for that particular winding, and since we have winding going from 1 to k, so we have correspondingly for every winding there will be fraction of area which will be allotted in the window area of the transformer core. So, what we see is that there will be a optimum value of this gamma j, for which the total copper loss will be the minimal, because as we see, as we increase our gamma 1, that means the fraction of the area allotted to the winding 1, if we increase that value, we see that the copper loss is reduces, is primarily because as our gamma 1 increases, the area allotted to winding 1 increases. So, for the same number of turns we can use a thicker conductor, and that is when our copper losses in the winding reduces. Similarly, at the same time, since our gamma 1 is increasing going towards 1, which is 1 means it is going towards the entire window area, that indicates that the area allotted to winding 2 to winding k is very less, and that is when, to obtain the required number of turn, the copper conductor has to be smaller in size, and which will increase the copper losses in the other winding. So, that is when we do the total copper loss, what we see is that there is a optimum value of gamma for which the total copper loss is minimal. So, one has to do the optimization to obtain the optimum value of gamma 1 such that the total copper losses, or you can say the total winding losses in the winding is minimal. So, this is what we have understood. So, in total what we understood is that we have to obtain the optimum value of gamma such that our PCU total will be minimal. We have to obtain the optimum value of peak AC flux density such that our total losses or total losses in the transformer is less, that means the summation of the core loss and the copper loss, and at the same time for that optimum value of delta B we can then calculate our number of turns in the primary winding, or you can say the winding number 1, and using the turns ratio expressions we can obtain the number of turns in the other windings as well. Now let us try to summarize the different points what we have done up till now. So, when we see the summary, there are some quantities which are specified quantities, that means they can be easily obtained from the specification, and there are certain quantities which we have to obtain, like for example particularly the core dimensions. Along with that we have to also obtain the peak AC flux density, primarily the optimum peak AC flux density such that our overall losses in the transformer is minimal. Similarly, we have to also obtain the wire sizes, or you can say the area of cross section of the wires, that also we have to find out, and then the number of turns, some things we have to find out. So, those were the design outcomes. So, let us try to see what are the specified quantities we have. So, if we talk about the specified quantities, what we have is we have wire resistivity. Again, it is dependent on the material of the wire. If it is a copper, then that has a specified value, and this it is defined by rho, and they can define using ohm centimeter. So, if it is a copper wire, then rho value could be 1.724 into 10 to the minus 6 ohm centimeter at 25 degrees Celsius. Again, it depends upon the temperature and the material which is being used to actually realize that particular wire. Similarly, the other specified quantity is depending upon the operation of the circuit in which this transformer is being kept, one can estimate the total RMS winding current, that means current in the winding, and that they can refer it to the primary side, or you can say the winding 1, which we can define the term called as the I total to be nothing but equal to J equal to 1 to K and Nj by N1 into I1. Now, using that this we can use this particular expression in this particular in this for this particular expression, that means Nj by N1 square into Ij square, to represent it to be I total terminology. So, that is what is the another one, which is the total RMS current referred to the winding number 1. So, this is the Ij. So, it depends upon the what is the RMS current in different windings we have. Now, this particular Ij you can for every winding you can calculate, and then you can refer it to the primary side to obtain the total RMS winding current what we have. Now, after that you can define the desired turns ratio. Now, this desired turns ratio you can obtain it depending upon the circuit operation and depending upon the nominal input and output voltages, and you can define it to be N2 by N1, N3 by N1 and so on, Nk by N1. So, this particular value is obtained using the operation of the circuit and knowing the sum of the specification input and output voltages. Now, after knowing these things, so this is the turns ratio which we will be using it to put it in this term and then obtain the total copper losses. Then another quantity which you can define is nothing but the applied volt second of winding 1, and depending upon the operation of that particular circuit in which the transformer is being kept. So, we can then write applied volt second of winding 1 and that we have already defined it to be a flux linkage which is nothing but V1 of t dt, where V1 is nothing but a arbitrary periodic signal, and this is for the positive portion of cycle, because if we consider for negative portion then overall it may lead to 0. So, we can just do it for the positive portion of the cycle, and this is nothing but defined in terms of volt second. Now, after this there is another specified quantity which you can define, which is nothing but allowed total power loss, which is, you can say, P total allowed in watts. And now this you can obtain by doing the loss budgeting of your entire power converter which you are using, and then you can define what could be the maximum power loss in transformer you can afford, and that is one of the specification you can define depending upon the overall converter specification. Generally power converter specification, the efficiency term has been defined. So, from there you can do different loss budgeting like semiconductor losses and passive losses, and then you can define the maximum power loss which you can allow in the transformer. Then there is another term which you can define the specified value winding fill factor, that is again Ku value, it is the constant Ku value, it's a small k, and this is again depending upon what kind of winding you are doing, depending upon the specification you can find out. And then core loss exponent, which is again beta, again depend 2.5 to 2.7 for high frequency ferrite materials, for different high frequency ferrite material it is in this range. However, most precise information you can get it from core manufacturer data sheet. Then you can also define core loss coefficient. This you can get it from core loss curve by doing the curve fitting in the core loss versus delta B curve which is provided by the core loss manufacturer, that is nothing but K core, and again this is a constant terminology. Now, these are some of the specified quantities we have which will be given from the different specification values. You can easily predict these are the specified quantities. Now, these are some of the quantities which you can obtain it from the specification, which you, depending upon the kind of material you are selecting, depending upon the kind of circuit you have, depending upon the operation of the circuit, you can define this quantity. Now, there are certain outcomes which you have to obtain. You need to find out certain quantities, particularly the core dimensions, peak AC flux density, wire sizes, then the specific number of turns. See, we have defined the turns ratio, but we have not defined the specified number of turns in individual winding. So, the design outcomes are, if you see the design outcomes, so design outcomes are nothing but your core cross sectional area, define it in as a AC, the term we have defined. Then we have core window area, which is WA, which we have defined. Then we have also seen mean length per turn, which is nothing but MLT. Then we have defined the magnetic path length, which is LC. Now, the moment you select a particular core, all these quantities will be defined in the core data sheet. So, these are the core dimensions. Then finally, we also have to evaluate peak AC flux density, which is delta B, and which is in the terms of Tesla. So, that is the unit of that delta B we are talking about, and this delta B is the one for which we are having the minimum total loss in the transformer. So, we have to then calculate the optimum value of delta B, and from there we can define the core geometrical constant, and from there we can then start our transformer design. So, after this we can then define our wire size. Obviously, here we are talking about cross sectional area of wire, that also has to be defined, because we will calculate the number of turns, we will know the mean length per turn, but still we do not know what is the actual size of the wire, and that we will define to be AW1, AW2 goes up to AWK for K windings, and along with that you also need to know what is the number of turns in each winding you need to have, such that you can obtain the required operation or you can obtain the required transformer. So these are some of the outcomes which we have to define. We have to define core dimensions, that means particularly we have to define which core size we have to select. We have to define the optimum value of AC flux density such that the total loss is minimal. We have to define what will be the size of the wire which will be using it to wound in the winding, and then we have to define the exact number of turns which will be needing in the different windings. And now once we know all those things, we can then physically realize our transformer, which we can use it in isolated DC-DC converter. Now let us define our transformer design procedure. Let us define our first step of transformer design procedure to physically obtain the transformer. Now in that, the first and foremost thing is we need to select the appropriate core. Select the core. That means let us say if we select the E base core, then we have several types of EE core. That means we have EE5, we have EE25, we have EE30 and so on. Now EE core means what I am talking about is this one, something like this. 2 EE cores you can take and put them like this, and you can place them on a bobbin, and over that bobbin you can do the winding such that you will get the required transformer. So the first and foremost thing is to select the required core. What will be the size of the core, whether it is a E5 core, E25, E30. So the first, let's say it starts with, we have to select the core. For example, let's say you have selected the E25 core. Your starting point is E25 core. Again, the transformer design procedure is not the single step procedure, it is a multi-step procedure. So we have to do several iterations to reach to a best possible transformer design. So the first and foremost thing is you select the required dimension of the core. Let's say you selected the E25 core. The moment you selected the E25 core, from the core data sheet what you can obtain is, you can obtain the area of cross section of the core, you can get the LC value, magnetic path length, you will get the mean length per turn value, you can get the window area. Now you have also selected the material of the core. So the moment you select the material of the core, you know your beta value, you know your K core value. So this is from the core material. From the core material data sheet, you can select the beta value and K core value. That. So this is the first iteration you have done. You have selected one core. I mean, depending upon design procedure, you can able to decide that whether that particular core is the smallest core or not, or whether we can further go below. See, our idea is what? Our idea is to obtain the best possible transformer design. That means we can able to obtain the smallest transformer design, because for that purpose only we are going for high frequency isolation in the isolated DC-DC converter, and at the same time we wanted it to ensure that the losses in the transformer will be as minimal as possible. So both the things has to be obtained. So that's why our aim is to obtain the smallest of the smallest core which need to be used to obtain the required transformer design. We satisfy the required condition, at the same time able to ensure that specifications are being met. So this is our step number 1. So with this, our first iteration, the values of AC, LC, MLT, WA and beta and K core is been obtained. So now comes the step number 2. In step number 2, what we will do is we will evaluate the core loss term, which is K core del B raised to beta ACLC. Now here we will do in terms of delta B. Still we do not know what is the delta B. We will just define this particular term with respect to delta B, because still we have not done optimization to obtain the optimal value of delta B. So we will just write our, we will just define our expression in terms of delta B. Then we will evaluate our total copper loss in the winding, or you can say total winding losses, and that is defined again, we will define this particular PCU total as rho MLT WAKU lambda 1 square 4 delta B square summation j equal to 1 to k and j by n1 square j square divided by gamma j square. Now here when we are defining the PCU total, we will ensure that this gamma j value is the optimum value of gamma j that means gamma j optimal such that the PCU total is the minimum value that we have to define. And this again, this particular thing is in terms of delta B. Still we do not know what will be the our delta B term. Now here when we are obtaining this optimum value of gamma j, we can apply certain optimization principle. Now one such optimization principle is defined in the references like Lagrangian multiplier optimization method, or someone can use the advanced optimization method to obtain the best possible gamma j, or to obtain the best possible fraction of area allotted to that particular winding, and that is when which will lead to the minimal overall total copper losses. So that is what we will get, and that is when P core and PCU total we have defined. Now after that what we will do is we will go to step number 3, where what we will do is we will do the optimization for delta B. So we will obtain the optimum value of delta B. Again one simplistic method is you can do it by doing P total divided by del V equal to 0, where our P total is nothing but our P core plus total copper loss. Now this will implies that what we will get is we get core by delta B. Now when we solve this thing, what we will get is we will get the delta B optimal. Now once we obtain our delta B optimal, so let me write down with what we are getting is we will get delta B optimum value. Here from here we will get the gamma j optimum value, and here we will get the delta B optimum value. After this we will go ahead and do the step number 4, where we will then evaluate. Once we know our delta B optimum, we can then obtain our P total value, which is the total loss in the transformer, which is nothing but PCU total, and this we will obtain it at delta B optimum point, which we have obtained in step number 3. So we can put this from the step number 3, this we can put it from step number 2, and we will get this value. At the same time we will get the P core value, which is obviously at optimum value of delta B. Now this P total value, which is the minimum value which we obtain at del B optimum, should be such that the P total value what we are obtaining here must be less than equal to P total allow, which is the allowed total loss in the transformer, which we obtain it from the loss budgeting, that means one of the specified quantity, which this is nothing but one of the specified quantities. So now what we have to do is we have obtained the delta B optimum value, and from there we calculated the P total, and this P total what we obtain is should be such that it is less than the allowable total loss in the transformer, that means it should be less than the specification specified value which we obtain it from the specification. And if this particular condition is not met, then what you can do is you can go ahead and then select the next big core, which is nothing but, let's say if we are selecting a E25, then the next big core is E30 core, and then again follow the step 2, step 3, step 4, and then again see at last whether your P total is less than P total allow or not. If it is not there, then again you go back and then again you select the next big core, and then this procedure keeps on going until you reach a point where you are obtaining the minimal total loss in the transformer less than the allowable loss in the transformer. And that is when it is a iterative process, it is a multi-step process. Now, the optimization need to be done such that to obtain the optimum value of delta B and the optimum value of gamma j, which is the a fraction of the area allotted to the windings, and so on. Now, once we know this thing, what we have is we have obtained our delta B optimum value. Now, this condition is actually defines, this condition defines whether the next iteration is to be done or not. Now, if this condition is satisfied, then we can go ahead and then define the step number 5. We can define the number of turns in the winding. Now, how we can obtain the number of turns? So, for that, for the first winding, we know that from our discussions in the previous classes, N1 is nothing but lambda 1 by 2 delta B AC, and here our this value is the specified quantity, that means depending upon the operation of the circuit in which this transformer is being used. This is the value from the selected core, from selected core size. This is the delta B optimum value which we obtain from the optimization in step number 3, and using that one we can calculate our N1, and from there we can calculate the N2 by doing the nothing but turns ratio, as our turns ratio of the specified quantity multiplied by N1. So, this is the specified quantity. Again depends upon the operation of the circuit and the nominal winding voltages which are been given. Now, after that you can again calculate N3, which is N3 by N1, again turns ratio between the winding 3 and 1, and then similarly you can do it for Nk, which is Nk by N1 into N1. Now again these are all the specified quantity. Now, using this what we can get is we can now obtain our N1, N2, N3 and so on Nk, and this will lead to the next step, which is to obtain the area of cross section of the wire, or what will be the wire sizes we have to select. So, we can now after this we can then obtain the area of cross section of wires by the formula, which is AW1 should be less than equal to gamma 1 optimum value into Ku WA by N1. There if you see, generally this is obtained from the core dimension, from the selected core, because once we select one core we know our WA. This is from step number 4 we obtain. This value we can obtain it from step number 2 by doing the optimization such that the total copper loss in the winding is at its minimum value, and this is nothing but the winding fill factor, which is to accommodate the area which got lost while doing the winding. For example, if we take the circular conductor and if we place them nearby each other, then still we will not be able to use the entire space which has been allotted to that particular winding, because this area is still vacant and we cannot use that. So, obviously we have to define a term called as the winding fill factor, which actually accommodates this area which will not be used, and obviously Ku is always less than 1. Depends upon what kind of windings these are been there. Also in the windings we have the enamel coating like this. We have enamel coating such that nearby conductors are not get short circuited or does not come in contact with each other. Now, if we place the windings like this with enamel coating in them, then there are some areas, obviously there are areas which is not been used. This is your enamel coating, so it is just a bare copper wire with the enamel coating, which is an insulation coating, and this is the area which is not been used, because they are circular conductor, they cannot occupy the entire square area. So, there are some spaces which are actually lost from the area which is been allotted to that particular winding. So that's why fill factor has to be considered, that portion of area has to be considered which got lost while doing the winding or by placing the windings in the area which has been allotted. So that is why if we see this gamma 1 optimum Ku and Wa is the area which is being taken up by the winding number 1, and this has to be greater than equal to the number of turns multiplied by the area which is being taken up by the individual wire, then only we can able to accommodate that many number of turns in the allotted area in that particular window of that particular transformer. Using this particular relationship we can get AW1, and similarly we will get the AW2 also by doing the optimal Ku Wa by N2, and so on. You can define for kth winding gamma k optimum Ku Wa by Nk. Now using this formula what you will get is, you will get AW1, AW2, you will get AW3, and then using this value you can then select the appropriate wire gauges. Generally wire gauges are defined in AWG or in SWG depending upon it is which part of the world, it is American wire gauge or it is a standard wire gauge, and using that thing you can select the appropriate wire gauge can be selected. It could be AWG 8, 10 and so on, it keeps on going, AWG 40, 44 also you have. So all those wire gauges there are there, from that list which is a very standard list, you from there you can select those wire gauges which satisfy this particular criteria, and then select the maximum area of cross section of the wire which satisfy this criteria. So using this one you can then select the wire sizes, and then using that you can actually able to then purchase the required wire size, and then you can use that to wind your transformer, because you already know number of turns, you already know what is the core size, and just you have to bought the required wire sizes and then wound it. Now in the entire thing what we have assumed is that we have assumed that the wire geometry and the skin and proximity effect are not there. That means we have already considered winding losses. What we have defined is just I square rho L by A, which is just the losses corresponds to the DC excitation, but generally these transformers are applied with high frequency AC. So accordingly that approximations can be taken and then required thing can be obtained. Similarly, we have not considered any wire geometry. What I mean by that is, we do not consider how the wires are laid down, particularly in case of Litz wire, we do not know that. So that part also is not being considered, or we have assumed that they are not there, and so that has simplified our transformer design procedure. Now one can also use other transformer design procedure. One simplistic way is to obtain the transformer design using the area product method. However, in area product method we assume that the flux swing is between the maximum positive Bmax value to the negative Bmax value. There we have not done any optimization where our overall losses is reduced. So this is the next kind of transformer design where we can reduce the overall losses as well. Now there are also another kind of transformer design procedures which are been there, where one can also accommodate the AC effects, the skin effect and the proximity effect, and then design the transformer according to that. Further, here we have assumed that the excitations are nearly sinusoidal excitation. One can also consider the excitation could be the square wave excitation, and then can generalize that particular the value of core loss using the improved Steinmann's equations, and can obtain the more real transformer design. So there are several transformer design procedures are there, where the simplest thing one is the area product method, where the maximum flux swing we have considered. However, in this case we have assumed that the flux swing is such that we will get the minimal total losses in the transformer. That means we have the optimum value of maximum flux swing, and that is when we will get the minimum total losses in a transformer. Similarly, one can also consider the skin effect, the proximity effects, or you can say the AC loss effects, and then can able to design the transformer design procedure. So, what we got following our design procedure, we have got the core dimensions, which is nothing but our AC, LC, WA, MLT value. Then we have got the peak AC flux density, which is nothing but delta B optimum value. We have also got gamma J optimum value, for which our PCU total is minimal or is minimum, and this is done for which the P total is minimal. Then after that we have got our AW1, our AW2, that means area of cross section of wires, and AWK. We have got number of turns N1, N2, N3 goes up to Nk, and that is when using these particular things we will be in a position to now physically realize our transformer. So, using all these particular quantities, we have all the things with us, we can select the required wires, we can select the required core, purchase the required corresponding bobbin, and then actually physically realize our transformer, and then put it in the converter in which it has to go, and then do the required operation. And finally, after doing that, one can then do, let us say, if the transformer, let us say if you have the transformer, if we draw the model of the transformer, so it is LM1 referred to primary side, IM1, let us say it is N1, N2, I1 current is going, and let us say resistance of the winding is 1, on the secondary side it is R2, and it is the output is going. Similarly, you have other windings as well. Let us draw the kth winding Rk, which has number of turns Nk. So, then we can then do a simple design check and see whether our values are within our required specification or not. So, for that what you can do is you can also calculate magnetizing inductance referred to primary. Here we are assuming the winding 1 to be primary. Let us say here we are applying V1 of t voltage. So, referred to primary, and referred to primary of winding 1, we can write LM1 to be mu, mu c, which is mu naught mu r times N1 square AC by LC. Okay. Similarly, you can then find out peak AC magnetizing current, which you can get it Im peak to be lambda 1 by 2 Lm. You can easily Lm1 refer to primary side, this is obviously referred to primary side. And then finally, you can calculate the winding resistances. Obviously, these are DC resistance corresponds to the DC excitation, which is R1, which is nothing but rho N1 MLT divided by A W1 goes up to Rk, which is rho Nk MLT by A Wk. Area of cross section of wire used for winding the winding number K. Now, using this thing, once you know the R1, R2, Rk, you can then evaluate losses, which is both core as well as copper, because all the dimensions and everything from the core manufacturer data sheet, you can calculate the core loss per unit volume, and since you have already selected these dimensions of the core, you know what will be the volume, and from there you can easily calculate the core loss, because you also know what will be your delta B, and obviously you know what will be the frequency of excitation of this V1 voltage. So from there you can easily calculate the core loss, and for the copper loss already in using the specification what will be the RMS current in different windings, and then we know the resistance, we can calculate the resistances for the different winding, and then we can do I square R loss. Again here we have not considered the AC effect, we have not considered the AC losses as here you can consider, and that will be another kind of design procedures you can look for. So you can evaluate the losses and then check if it is within the allowed limit of power loss, or P total allowed, which we have already considered in, which is one of the specified value which which you can get it by doing the loss budgeting of your converter. You can define this much loss I can afford to have it in the transformer, and then you can define the core dimension, number of turns, area of cross section of the wires used for wound the windings, and then from there you can calculate the copper loss, and then you can do the summation of both the losses and then see whether it is within the specified limit or not. If it is there, then it is good. If it is not there, then you go back and select the next big core, then you can see as for now we have selected K at E25 core. So you can then select E30 core and then repeat those steps to calculate the number of turns, to calculate AW of the wire, or you can say wire cross sectional, and then to calculate the delta B, and then finally do the checking and then see if it is okay. Then you can use that core and winding to actually physically realize your transformer. So transformer design process is a multi-step approach, and here again we have not considered the AC effects, or you can say the losses corresponding to the high frequency ACs that we have not considered. You can also select that, and you can then understand what could be the pattern with which you would like to wound the winding, how far those windings to be placed, and number of turns to be defined in different winding layers that can be defined, and then accordingly you can you can design, you can physically realize your transformer. This is all about transformer design. In the next lecture we will see the inductor design, and that's when we will cover up this portion on the transformer design, where we, because these designs are important, because in our is the isolated DC converter we are extensively using these transformers and DC inductor to perform the required operation. Thank you very much for patiently listening to this lecture. We will meet you in the next lecture.